Hello and welcome to the 6.3 video. This is part 4, and we're going to discuss a similar method to what we had with the disk method, but we're going to call it the washer method, okay? And so first let's zoom in on this object here, and this is what we'd call a washer. And what a washer is it's a big cylinder with a big hole in it, okay? And so what I want us to do is to come up with a formula for the volume of this cylinder. And so what we would do is we would take the volume of the big one, which is pi times this radius 2, so r sub 2 squared times the height. And then we would take the volume of this inside cylinder and subtract it from the larger one to leave us with the volume of that washer. So I'd want to subtract off pi times r sub 1 squared times the height. Now, what I can do here is that I have a common, some things I could factor out. I could factor out a pi and an h from each of those terms. So I could say that the volume is equal to pi times the height times r sub 2 squared minus r sub 1 squared, okay? Now, for our purposes, what we will need to do is, because we're multiplying all of these things together, we can rearrange this. And so I want to write my volume as pi times r sub 2 squared minus r sub 1 squared times the height, okay? Doesn't really matter what you do. I'm just doing this because this is going to help us set up our integral. Okay, so now I do want to show you guys something. R sub 2, this is our big radius. Okay, this is our big radius. Okay, and then r sub 1, this is our little radius. And it's important that we understand that, because we're going to have to use that terminology later. But let's go ahead and move on from here. And it says, first, okay, let's set up an integral to find the area of the shaded region. This is still that same thing from the previous page. So our area here would be to take the integral from a to b of f of x dx. Now, just to remind you guys that f of x is the height of a very, very, very thin rectangle. Okay, this is the height of that rectangle, and the dx is our width. Okay, so now what I've got is we're going to go ahead and rotate this region. But before we do that, I want to take one of those little rectangles. And the difference is that our axis of revolution is no longer the y-axis, or the x-axis. It's going to be the line y equals -1. That's our axis of revolution. Now, when I change that axis of revolution, when that axis of revolution is not touching my function all the way across, when I rotate that rectangle around, it's going to give us a washer, okay? And so, and that's what I want you guys to see, is that when we rotate this around, we get that piece that's missing inside around that axis of revolution. So when you change the axis of revolution, and when it does not hit the shaded region, then you will get a washer. Okay, you get that space in between. Okay, so what I want to do is I want to now write an equation that would represent the volume, okay, of the following cylinder, given that f of x is equal to the square root of x, and the axis of revolution is y equals -1. So the volume of this washer, okay, and we're going to use what we had before. We're going to do pi. But now what I want to do is identify what my big radius is. Okay, so my big radius, and so my big radius is the distance from my function to the axis of revolution. Okay, And so that's going to be the distance, the square root of x minus negative 1. Okay, so that's just going to be the square root of x plus 1. So big radius r is equal to the square root of x plus 1. Okay? And then let's find our small radius, and that's the distance from the small function, which is the x-axis, to our axis of revolution, and that is just 1. So our little radius is just 1. All right? And so I'm going to start using that terminology of using the big R versus little r. This tells me my big radius. This is my little radius. And so what I'd want to do is I'd want to write it like this. I'd want to say the quantity, square root of x plus 1, that whole thing squared, minus my little radius squared. So minus 1 squared. Okay, close that up, and then we'd multiply that by delta x, which is the width. That's our change in x. Okay? So I want you to see that this formula here is the same thing that we have here. This is our big radius. This is our little radius. Okay? So now let's take a look. All right, it says, similar thing to what we had before. If I stack a bunch of these washers on top of each other that go underneath that function, okay, the radius of each of these changes. Okay, and the radius changes. It depends on x. Okay, depends on x. Okay, so what would you have to do to add up an infinite number of these cylinders? Okay, you would have to set up a definite integral. Okay, and we can quickly just take a look at what this would look like. Little animation real quick so we can see what's happening here. When you rotate that around, you get a washer, okay, and you get this space in between, and then we've got all these other washers, okay? So, we can do this for one rectangle, and we can model that and show that we can show that they all have different radiuses. So just like the disk method, okay, the radius of each of these disks changes, okay, and same thing with the washers, all right? So let's go ahead and let's take a look at something else. And let's take a look and see what this would look like, okay? So if I take this region, this exact region, and if I rotate that around the axis of revolution, which is y equals negative 1, then what we see here is that we have the space that's missing from the inside, okay? And so we have to set up these integrals a little bit differently, but the concept is the same. We're just adding on another step, okay? Now the trick with these is that you have to identify whether or not your axis of revolution touches your shaded region or if it doesn't touch, okay? If it touches that the whole way across, you use the disk method, but if it doesn't touch, then you have to use the washer method. Okay, so let's go ahead and let's set up a definite integral here to show what we're doing. All right, so let's go ahead and set up this definite integral to find the volume of this solid, okay? And the function, we are doing this over the function y equals the square root of x, and this is the axis of revolution is y equals negative 1, okay? Now, the thing that I do is I look for my big radius for my washer and my little radius, okay? And I'm going to call it big R of x and little r of x. And what I do to find big R of x, and let's write this out, okay? Big R of x is the distance from the axis of revolution to the furthest function, okay? And so that's something where, depending on where the axis of revolution is, that's how we determine big R of x, okay? Our axis of revolution in this case is down below, but that's how we figure that out. Now, little r of x, okay, little r of x is the distance from the axis of revolution to the closest function. Okay, and those are the things that we have to remember. This is what I will always be saying in my head because these are the pictures that I draw, okay? So the first things first, I'm going to go ahead and draw big R of x, and I'm going to go from my axis of revolution, start here, and draw a line perpendicular to my axis of revolution all the way to my furthest function, and I'm going to call that big R of x, okay? Then what I do is I have to draw my little r of x. And that's from my axis of revolution to my closest function, which is the line y equals 0. Okay, I'm going to call that little r of x. So then down here I'm going to say big R of x is equal to, and we got to find that distance now. And so I have to do top minus bottom. So I have to do square root of x minus -1. And we've already kind of found that, and that's just going to be the square root of x plus 1. Okay? And then our little radius, little r of x, is going to be the distance from the axis of revolution to the y-axis. And that's just a distance of 1. That doesn't change. That's kind of nice. So then let's go ahead and set up our definite integral here. Same thing as what we would usually do. And so this is going to be volume is equal to the integral from a to b of pi times our big R of x, quantity squared, minus our little r of x, quantity squared, dx. Okay? So if I sub those values in, then I get volume is equal to a to b, pi, quantity, okay, big quantity. And then I have to do my big R of x, so square root of x plus 1, that quantity squared, minus little r of x, which is the quantity 1 squared, that whole quantity, then dx, okay? And that will give us our volume, all right? And so that's kind of, this right here, folks, is your formula that we're going to use for the washer method, okay? So it's pretty similar to the disk method, it's just that we have this little added thing, okay? So let's go ahead and take a look at example 4, okay? And it says that the volume, so find the volume by the washer method. Okay, the region R is bounded by the graphs square root of x and x squared between x equals 0 and x equals 1. What is the volume of the solid that results when R is revolved about the x-axis? So let's go ahead and just graph those. Okay, it doesn't give us a graph or anything, so I'm just going to draw a graph between 0 and 1. And I know that when I plug 1 in for x into either of my functions here, I'm going to get 1. So I'm going to plot a y value of 1, okay? And I'm going to plot that point, 1, 1. I have the square root of x that looks like this. And then I have the equation x squared that looks like that. So this is f of x equals the square root of x. This is g of x, which equals x squared, okay? Now, we are going to revolve this around the x-axis. And I want to show you guys what that figure is going to kind of look like. It's kind of a weird shape, but I'm going to go ahead and show you this animation real quick about what this would look like. And so if I revolve this, okay, if I take this, this region here, okay, and if I revolve that around the x-axis here, then I get this shape with, it's kind of like a bowl shape that has kind of a weird like cave to it, okay? So it's a really odd shape, but we can calculate the volume of this, okay? And so you kind of get an idea. It's like this bowl shape with another kind of like, looks like an instrument horn coming out of it. So just something that's kind of unique, all right? But because I have this space taken out, I have to use the washer method, okay? So let's go ahead and pause that and get out of this. And let's go back over here. And so first things first, okay? my axis of revolution is my x-axis, okay? So I need to find a big R of x, and then I need to find a little r of x, okay? So remember, my big R of x is the distance from my axis of revolution to the function that's furthest away, okay? And that's big R of x, okay? Now, little r of x is the distance from the axis of revolution to the closest function, all right? So that's little r of x. Now, what you can do here, if you'd like, is you can come in here, you can draw your own little slice, and you could do, let me just draw a slice like right here. That's not very good. Let me draw one right about here. And what I can do is we get this slice here, and we get this washer, okay? And I recommend drawing this just so you know kind of the idea. But again, main thing is draw your big R of x, draw your little r of x. So big R of x is going to be equal to that distance from the top function to the axis of revolution. So that's just going to be the square root of x, okay? And little r of x is going to be the distance from the axis of revolution to the closest function. And that's just the distance of x squared, okay? So if we wanted to calculate our volume here, all right, volume is equal to the integral, and we're going from 0 to 1 of pi, and then I want to do our big radius squared, okay? So I'm going to do the quantity, square root of x, that quantity squared, minus our little radius, which is going to be just x squared, quantity squared. Close that quantity, okay? You must have parentheses around these two radiuses, the difference of these two radiuses squared, and then have the dx on the outside. And that's it, okay? So it is kind of an interesting thing that we have to do, but all of these problems are very similar in the fact that we got to find our big R, got to find our little r, figure out what those distances are, and then set up our integral, okay? So I'm going to go ahead and stop this video. Hopefully you enjoyed it. Hopefully it was beneficial for you, and we'll see you later. Thanks. Bye.